begin where you left off last class, and that's with figure one, which we call a two-port network. Two-port, why? Because there's an input, and there's output. So let's call it a two-port network. And if you can have a two-port network, then you can have a three-port network or a four-port network. But right now, we're only considering a two-port network. Okay. You are used to seeing that. You are used to seeing the two-port network, okay, as in figure two, for example. Just how we didn't call it that. Figure two. What is figure two, by the way? What is figure two? Wow.
I know the time domain.
Folks, I think you all gonna graduate not knowing anything. We did this way back in 235. Some water. What kind of circuit is this?
Is that like a transfer function?
It is a transfer function. But what kind of circuit is it? Transfer function of what? No. This is not a transfer function. This has a transfer function. Transfer function of what?
Probably a low pass, or high pass filter.
Which is it? In fact, this is the first order low pass filter. Let's cut off frequency. Omega C equals 1 of RC. That's what you like. That's what you discovered in 235. Okay. So this then is our two-port network. The thing in the box. A two-port network has input V1 of t and V2 of t, or more generally, we could say X of t and Y of t. Okay. So as Mr. Beauchamp said, a two-port network has a transfer function. All right. We have a transfer function, but that's defined in the Laplace domain. Actually, this circuit here was defined in the phasor domain. If you cast your mind back to 235, okay, and this would be the transfer function, this G, okay. So this is figure 3. This is phasor domain equivalent of figure 2. Okay. And G was what? What was G? What was the transfer function? What was the transfer function? It was the output phasor divided by the input phasor. Okay. Or in other words, V2 phasor is equal to G times V1 phasor. Okay. This is what we did. All of this is what we did in 235. Okay. The problem with this though is V1 phasor has to be a sinusoid. Now let's come to today's class. This is no longer a sinusoid. The input is no longer a sinusoid. The input could be any function, but we convert to Laplace. So this now is V1 of S and V2 of S. And then G of S will be V2 of S, V1 of S. And now the output would be V2 of S equals G of S times V1 of S. So what am I saying? I'm saying it's the same philosophy. Except that now, instead of talking about phasors, we're talking about Laplace transforms. Okay. So let's get the transfer function for figure 2 then. Let's get the transfer function for figure 2. So we have to convert to Laplace domain. R remains R. What does capacity become? What does capacity become?
4 of S.
The input is V1 of S, and the output is V2 of S. Okay, so this is figure 4. Go ahead.
Before you go too far, can I take a screenshot of the first page? Sorry about that. Yeah. Thank you.
Okay, so figure 4 is Laplace domain equivalent of figure 2. Okay. Now that we're all here, well, let me see if he's locked in yet. No, I don't see his mic yet. His mic hasn't showed up. Mr. Anderson, can you hear me? Mr. Anderson, can you hear me?
Good morning. Yes, sir.
Morning. Now that we're all here, I want to remind you of the final exam next Friday, during class time, face to face. Okay. I want to remind you, you will not be able to use any devices except a separate calculator. Not a calculator on your cell phone, a calculator that stands by itself. Okay. Now, I know the government has lifted the mask mandate for classrooms, but I really would appreciate it if you would wear a mask for my sake. If I should get COVID, I will have serious consequences. So I would really appreciate it if you do me this favor. All right, we will try to meet in T19, just like the midterm. And just like in the midterm, I would want you to, after the exam is done, I would want you to send me a PDF file, just like we did in the midterm. Okay. So some of you need to practice how to do that on the device that you will have next Friday in class. Because some of you spent lots of time after the exam was done trying to send me a PDF file. We don't want a repeat of that. We want you to practice before next Friday. All right. Any questions about this? Okay. Let's get back to this. So figure 4, this is the Laplace domain equivalent of figure 2. Okay. So here's the two-port network. So what is V2 of S equal to? What's V2 of S equal to?
That's equal to 4 over S over 2 plus 4 over S multiplied by V1 of S.
What's G of S then? What's G of S? What's the transfer function? Folks, I just gave you this answer
Yeah,
on the
that's
first. Go ahead.
can't remember now. I think that's V2. So that's 2. That's the same answer we got over.
V2 of S divided by V1 of S. That's G of S.
Yeah, could we just write that answer V?
Therefore, what's V2 of S? So this is 2S plus 2 V1 of S divided by V1 of S. V1 of S cancels V1 of S. Even as it's 2 of S plus 2. That's the transfer function. And by the way, that's the same transfer function you would have gotten in 235 as well. All right. So, yeah, go ahead. No, you're reading that wrong. This equals this. That's not V1. But that ain't what you said. You said V1 of S equals that. is this multiplying V1 of S that equals that?
So graduate 8, then the first page. Quickly,
I thought multiplied by 2. I divide the top and bottom by 2. 4 divided by 2 is 2. 2s divided by 2 is 1s. 4 divided by 2 is 2. Simple grade 9 division. Okay. Anybody else?
so graduate, you could go back to the first page quickly, please.
No, Mr. Anderson, you joined late. You're gonna have to get that information from somebody else.
No man, just a quick glance.
Mr. Anderson, I do not reward people for coming late to my class.
Oh man, I no reward. That's just me looking at the page.
Get it from a fellow student. All right. Now, let me now define impulse response. What did I say impulse response was? Last class, what did I say impulse response was? Wow. Well, you all don't retain anything, do you?
And that's when you say the input is a pulse, is an impulse.
So what is impulse response?
Impulse response is the output of the output when the input is an impulse.
Yes. So we put a delta of t here. Okay, then the output is by definition the impulse response, which we call g of t. Impulse response. Okay. So it'll plus domain. What does that become? That becomes g of s on the output. Well, let me just put v2 of s then. All right. This is 2, and this is 4 over s. And we already found out that this was g of s. And there's v1. What's v1 of s? What's v1 of s?
By 2 over plus 2.
v1 of s.
That's just one.
Thank you very much. v1 of s is Laplace of v1 of t. I mean, how is it y'all don't know that by now? So what's the output here then? What's v2 of s equal to? What's v2 of s equal to? Wow. Folks, look on page 1 of your notes. No. Look on page 2 of your notes.
We already
What's
saw,
V2 of S equal to?
that's 2 over S plus 2 times V1 of S. And you said, not you said.
All right. I'll go with that. It's G of S times V1 of S. This is the general equation. This is always true. For any circuit, this is true. Okay. Now the input is 1. So V2 of S equals what? G of S times 1, which is G of S. Okay. So what's V2 of T? What's V2 of T? G of T. G of T. And G of T is what? The impulse response. So G of T, the impulse response, is the inverse Laplace of G of S. Okay? The impulse response, if you didn't learn anything today, learn this. The impulse response is the inverse Laplace of the transfer function. That's the big deal. That's what I just showed you. Get that through your head. The impulse response is the inverse Laplace of the transfer function. All right. So what we got then? Here's what we have. Here's V1 of T. Here's a 2-port network that with the impulse response G of T. And here's V2 of T. All right. Corresponding to this in the Laplace domain, so this is time domain. This is time domain. Okay. And this is the corresponding Laplace domain. Okay. And how is V2 related to V1 in Laplace domain? How is V2 of S related to V1 of S? We just did this, folks. We did this twice already. How is V2 of S related to V1 of S?
V2 of S is the transfer function multiplied by V1 of S.
Thank you very much. That's the key. You must always remember this. This is just like V phasor equals the transfer function. V out phasor equals the transfer function times VI phasor. That's the same rule, except that this is dealing with phasors, and this one's dealing with Laplace transforms. So how is V2 of t? How is V2 of t related to V1 of t? How is V2 of t related to V1 of t?
V2 of t equals G of t.
Come on. Is G of t the input?
No.
Don't you see that this is the input and this is the output and this is the transfer function?
I see that, Bob.
How is the output? Excuse me? Excuse me?
Oh, I didn't say none.
Now, here's what I expected you to say. Although one more try. What is V2 of t relative to V1 of t? How is V2 of t, how is the output in the time domain related to the input in the time domain?
The V2 of t, the output, is equal to the impulse response.
Really? That's it? Are you all not seeing the symmetry here? Don't you see V2? V2 is the output, okay? And the output is related to the transfer function times the input. That's the Laplace. That's in the Laplace domain. But in the time domain, V2 of t is related to what? Somehow is related to V1 of t and G of t. I mean, how do you miss that? So here's what I expected you to say. Here's what every other class I have ever taught, and I've taught this course now for the past 30 years, has told me. V2 of t is G of t times V1 of t. And I totally understand why they said that. I totally understand why they said that, because V1 of S corresponds to V1 of t. G of S corresponds to G of t. V2 of S corresponds to V2 of t. Unfortunately, this is wrong. This is wrong. Why? Multiplication in the Laplace domain is not multiplication in the time domain. As a matter of fact, these are related mathematically by something we call convolution. There's a new word for you. You have no idea what convolution means. Convolution is this. We won't be using it. We won't be using it. Convolution is an integral 0 to infinity G of tau times V1 of t minus tau d tau. convolution is this horrible looking integral. You don't have to worry about doing this. What you need to know, though, is multiplication in the Laplace domain is convolution in the time domain. Even if you don't know what convolution is, it's another mathematical process, another mathematical operation involving an integral. I just don't want you writing g of t times. This is not times. This is convolved with. G of t is convolved with v1 of t. Okay. But that's not how we're going to handle it. How we're going to handle it is v2 of t is going to be the inverse Laplace of this product. Inverse Laplace of g of s times v1 of s. That's how we're going to handle v2 of t. All right. That's a lot to take in. That's why I keep telling you, you must study after every class. Let's get back to our example. So our example is this. So here's v2 of t. Is v1 of t. Okay. The two-port network has a g of t, an impulse response. Okay. Corresponding to this in the Laplace domain, and there's g of s. And we have already determined for this g of s equals 2 over s plus 2. Okay. So what's g of t then? Yeah, go ahead. Right. Yes?
You breaking up.
Really? I didn't say anything. Am I still breaking up?
Not at this moment, no, but when you was writing the circuit and talking, you was breaking up.
All right. What about this circuit you don't understand?
No, I understand what you were doing so far. I just was telling you, giving you a heads up before I miss anything else.
Yo, man. I can't do anything about the moment I'm breaking up. Okay. You have to tell me right away after I'm breaking up. Okay. So I won't go on. Can you hear me well now?
Yeah, it seems clear now, yeah.
Okay. Anything on this page gives you any concern? I am just repeating what we did today in today's lesson.
I know, I'm following.
All right. Anybody else? Anybody else has trouble seeing what I've done? So what is g of t equal to? What's the impulse response equal to?
Isn't that 2e to the minus 2t?
Absolutely. The impulse response is the inverse Laplace of g of s. And in that case, this is inverse Laplace of 2 over s plus 2, which is 2 e to the minus 2t u of t. That's the impulse response of this circuit. That's the impulse response of this circuit. So that's something you learned today. Transfer functions, you should have known V of S, the output V2 of S divided by the input V1 of S. We know that from 235, but in 235, we were talking about phases. So the only new concept today is impulse response. An impulse response, I just showed you how to get impulse response. Get the transfer function first, and then do the inverse Laplace, and you get the impulse response. Or another way of doing it is put an impulse on the input, and the output would be your impulse response. Okay. Now, believe it or not, we could do question 1 of last year's final exam. But before I show you that, let's do one more question. One more example. What number I'm at? So this is figure 9. This is figure 10. All right. So this is figure 11. So this is example 2. This is example 2. Question A. Find the transfer function. What do we need to do to find the transfer function? The question B is going to be find the impulse response. All right, what do we need to do to find the transfer function? Wow. So nobody understood what I did today.
The transfer function is G of S. And to find G of S, you'll have to find V2 of S divided by V1 of S.
So what's the first step we need to do then?
First step you do is probably you have to cross the B.
The second person is talking. Let me hear from that second person, please.
Can we redraw the circuit using Laplace domain?
Not can we must. We must. That's the very first step we must do. Why? Because we need a diagram that has V2 of S on it. Because the transfer function is only defined in the Laplace domain. The transfer function is not defined in the time domain. So let's do that. V1 of t becomes what? What does V1 of t become?
V1.
Somebody said something? V1 of t becomes what?
V1 of S.
All right. And the inductor becomes what?
Could we use the same formula but just change the C with L? So 1 over SL? Would that apply?
Why is it you don't know this the answer to this question? Is that what we did with phases?
Would it be SL?
S or what? 2S? With phases is J omega L or SL. What does capacity become?
1 over SC.
Which is how much?
At 1 over S.
Really? Y'all can't even divide? Is that what y'all telling me?
That's just 10 over S.
Thank you very much. Now, how are we going to find V2 of S? Miss Danson, is this a voltage divider?
I would believe so, because that's what.
Really? The voltage divider requires two things in series. What two things you have in series?
You have two voltages in series.
Don't talk.
Two resistors. Whatever.
There's only one resistor in the circuit.
So yeah, we can use it then.
Folks, can we make this a series circuit? Can we make this a series circuit?
Probably you short of the positive.
Well, your circuit analysis skills suck to the uttermost. Is it not obvious to you that the capacitor and the resistor are in parallel? That's not obvious to you?
Yes.
So that is one. Let's call it Z2. Z2 is simply what? 10 over S in parallel 5. And now we have a series circuit. I mean, you should know this from 110. So Z2. Okay. Z2 is 10 over S times 5 over 10 over S plus 5. Multiply top and bottom by S. 50 over 10 plus 5s. Divide top and bottom by 5. Okay. And so, using the voltage divider rule, in figure 13, V2 of S equals how much?
V2 versus 10 over 2 plus S over
Yes?
2S plus 10 over 2 plus S.
That's it?
Multiply by the input voltage.
Yes. Now multiply top and bottom by S plus 2. And please take a screenshot because I'm going on to the next page. Okay. So just rewriting what I have at the last. I'm going to divide top and bottom by 2. So what's the transfer function then? What's the transfer function?
The transfer function is the same answer you got divided by V1 of S.
Yeah, so this is V1 of S. Divided by V1 of S. That cancels. So that's G of S. So G of S is 5 over S squared plus 2S plus 5. That's G of S. That's the transfer function. What order is it? What order is this?
That's third order, low pass filter.
Young man, where you get third from?
Not third.
I don't know why y'all have trouble identifying the order. I honestly can't understand why y'all have trouble identifying the order. What is the highest power of S?
Yeah, the second order, low pass filter.
Second order. Second order. How do you know it's low pass filter?
No, I know.
No, actually, it is second order, but I don't know how you knew that. You were just guessing it. But it is second order low pass filter. Excuse me? Did somebody say something? It's the highest power of S. And not only that, you can look at the circuit. 2 energy storage devices. 2 energy storage devices, therefore it's second order. There's an S term for each energy storage device. Now, having said that, What's the order of this?
That's one inductor up to the top or two.
That's two.
So that's by your explanation, that should be four order.
No, this is one inductor and this is one capacitor.
Oh, I thought you was counting it. Sorry.
Yes, I'm counting the distinct inductors and the distinct capacitors. Two capacitors in series is one capacitor. Two inductors in series is one inductor. So this is also second order. Okay. That's the side. Now what's G of T? What's the impulse response for the circuit?
Inverse of Laplace, open bracket, G of S, close bracket.
Yes. Then what is that equal to? What is that equal to?
But we have to further.
Somebody said something. You broke up. Please try again.
I was wondering if we would have to like simplify it some more or factor out the bottom, the denominator.
Young man. I don't know why y'all don't know how to do this. We've done this many, many times. This should be second nature to you by now. You folks do not study. You do not practice. Studying is not just reading over your notes. Study is trying problems, trying to work out problems. There's plenty of problems in your textbook with answers at the back of the chapter, back of the book. Now, why is it y'all don't know how to do this?
I think I saw a familiar question. Earlier when I was reading my book, S plus 1 squared plus 4.
You can rewrite that as that, but how does that help? Yeah, you just complete the square. That's all you're doing. How does that help?
I know for sure this K-street. Me using partial fraction expansion.
Say again, Miss Beauchamp.
I say this is like K-street.
It is case 3, and so how do we handle case 3? It is case 3. So the roots. What are the roots? What are the roots, Mr. Beauchamp?
-1 minus J2. And -1. Yeah.
So what then?
You could use the formula the Q of S.
Thank you very much. Q of S equals what?
Right now. Q of S is the numerator, not the numerator, F of S. And that's in our case is it's 5.
Yes, it's 5. Evaluated what?
The positive 1, so that's -1. S equals -1 plus J2.
And how much is it equal to?
That's equal to you have to put that on the extra. Oh, let me do it quick. That could be the square root of 10. No, not 10. Let me see. And it was 2 square root 5.
Yeah, man. Q of S equals 5. no matter the S value. Q of S does not depend upon S.
Oh, yeah, because you know we're asking in numerator and the numerator.
I don't know what, man, I don't know what you all talking about degrees for. Why y'all talking about degrees? Q of S equals 5. For any value of S, Q of S equals 5. I don't know why y'all have difficulty with this. There's no way to substitute S equals -1 plus J2. S is not part of Q of S. In this example, it is simply 5. And 5 is simply 5, 0. So M is 5 and theta is 0. Therefore, G of T equals how much? G of T equals what? M divided by omega. What's omega?
Our omega was 2.
Yes? Yes? E to the minus T sine 2T plus 0. So G of T equals 2.5 e to the minus T sine 2T. Okay, that's one method of doing. Excuse me, go ahead. Go ahead. No, you don't. Well, then you don't know how to find it. I don't know why students try to bullshit me about what they know. If you ask me where I got it from, then you don't know how to find it. It comes from the root. This is negative alpha plus j omega. All right, that's one way of doing it. What's another way of doing it? Let's go back. What's another way of doing this? What's another way? Using the Q of S method. That's one way. But I taught you at least 2 different ways. This is entry in the table. This is an entry in the table. Okay. But we would have 2 up top. We'd have 2 up top, and so not to change it, this has to become 5/2. Okay. So this entry in the table is, instead of S, this would be sine. This is sine, except it's being multiplied by e to the minus t. So this here is the inverse Laplace of this is, we call this y of s. No, this is g. This is g of s. Okay. So g of t is 5/2 e to the minus t. That's because of this. Okay. Sine omega. That's omega squared. That's omega 2t u of t. That's the entry in the table. That's another way of doing it. All right. Now we're ready to tackle question 1 of last year's final exam.
Other guy, what did you say just now?
Now we're able to tackle question 1 of last year's final exam. So everybody, please look at last year's final exam. Question 1. Everybody got it? Let's use n equals 10. Okay. So we're talking about Laplace transforms. Therefore, we need to show what? We need to show the Laplace circuit. And the Laplace circuit would be what? What does capacity become? One over 2. Folks, how is it we've done now what? 3 or 4 examples and we don't know the Laplace impedance of a capacitor? 1 over 2s. Excuse me? Go ahead. Young man, what you're asking is what's the Laplace impedance of an inductor? That's what you're asking. And let me ask you another question. When we were doing phases, what was the impedance of the inductor? I don't know what y'all doing when I'm teaching. I told you this about half an hour ago. I told you this when we were doing this example.
At JWA. J omega.
There ain't no freaking W.
J omega.
Thank you.
J omega L. That's the formula.
J omega L, and that's from the phases. And we just changed J omega to S. That's why I did it back even in 235. I did it back in 235. What figure number are we up to? Okay, figure 13. All right, what's the question? Find an equation for the Laplace of the output voltage. All right, how are we going to do that?
You see, they give us V1 of T, the value.
Therefore, what are we going to do with that?
Find the Laplace inverse.
Really?
Not the Laplace. You have the call it now. You have to convert it to this one.
To what? What we have to convert it to?
To Laplace.
V1 of S, which is how much?
10 over
S plus 1.
S plus
S.
S plus 40. What's 4?
S plus 4.
Yeah.
Mr. Johnson living in La La Land.
No, I had to correct myself. I needed to zoom in.
All right. It says what? Find an equation for Laplace of the output voltage. All right? How we can do that?
The resistor, 10 ohm resistor, and the impedance of the capacitor in parallel. Work that out first.
All right. So this is, let's call that Z1. All right. So we simplify. And what does that give us? So Z1 equals 10 and parallel 1 over 2S. It's 10 times 1 over 2S over 10 plus 1 over 2S. Multiply top and bottom by 2S. Okay. Divide top and bottom by 20. Okay. So we got Z1 of S. So what's V2 of S?
We could use the voltage divider.
Yes. You see, this circuit is not a voltage divider, but we turned it into a voltage divider. So V2 of S equals how much?
2 ohms over 0.5 over S plus 0.05 plus 2.
Yeah, man, did you break up? Or I didn't hear. Oh, you said it wrong. What's on the denominator?
The denominator is 0.5 over S plus 0.05
Nonsense. You don't know voltage divider rule.
plus 2.
Ah. That's it?
Times V1. Yeah, V1 of S. Sorry.
10 over S plus 4.
All right. So this first one, we can simplify by multiplying top and bottom by S plus 0.5. So 2 times S plus 0.05. Okay. Divide by 2 times S plus 0.05. Okay. Times 10. Sorry, plus 0.5. Times S plus 4. So take a snip, please, because I'm going on to the next page. So V2 of S becomes 2S plus 0.01 times 10 over 2S plus 0.01 plus 0.5 times S plus 4. So that's 20S plus 0.1 over 2s plus 0.51 times s plus 4 equals 20 s plus 0.1 over 20. Zero point zero zero five. Okay. Over 2 s plus 0.51 over 2. Point 255 s plus 4 equals 10 s plus 0.005 over s plus 0.255 over s plus 4. And you see I've done what the question says. This is K, this is C, this is A, and this is B. So I answered what the question said. What order is this filter? What order is this filter?
First order.
Yes, this is only one energy storage device. Okay. So on the final exam, you can now do 1 and 2. Okay. And how much time we have left? We may be able to answer question 3 before the end of this class, but we'll see. Okay.
Mr. Cartwright, is it possible for you to go over your enter like the Laplace circuit and the piecewise?
What does that mean? You can't simulate. You can't simulate. You can't simulate the Laplace circuit in piecewise. You can simulate the time domain waveform, the time domain circuit. You can simulate figure 1 of this exam, but you can't simulate. You can't simulate the Laplace circuit itself.
No, because I was trying it on a homework, but it wasn't doing.
I don't know what that means. What was the question asking?
No, not on this test. I talked about on the test you sent us.
Oh, I'm not going to give you the answer that I'm asking you to do. I'm not going to give you the answer to the question I'm asking you to do.
Not the answer, like a demonstration.
Yo, man, I have demonstrated this over and over. I have demonstrated how you simulate that circuit in piecewise. And I'm only asking you to demonstrate the circuit for t greater than 0. So the switch, I forget the homework. The switch is either going to be open or closed. So you don't have to put the switch in.
No need to put it in, all right.
Why would you need to put it in? I'm only asking you for the t greater than or equal to 0 plus simulation. So the switch for t equals 0. I think it closes. I forget. Let me see the. I don't know why I have to tell you all this.
Do we use the V sign? The V sign wave?
I don't know. I can't remember what I asked you.
Yeah, it was the sine wave.
Let's see. Yes, okay, I see the circuit now. What's the problem? I'm only asking you to simulate for t greater than 0 plus. T greater than or equal to 0 plus. So the switch is closed. So why would you have to draw the switch? You just draw a short circuit. Is that clear?
Yes, sir. How would we set up the V sign on the
Young man,
P-switch?
you ain't serious. How you set up the V sign? That's what we've been doing all semester. That's what we did in 235. I ain't going over how you set up the V sign. If you don't know how to set up V sign, you ain't been paying attention at all semester. And I'm not gonna go over that. Yeah, I suggest you ask a classmate.
What if no one in the class know how to do it?
Well, then the whole class should fail this course. And I'm serious about that.
But all the guy already walking like we use P-Spice on the regular. We don't though.
I don't care if you use it regularly. Once I show it to you once, you are responsible for knowing it. And if you don't know it, it's because you didn't study it when I gave it to you. I suggest then you Google it. I can't believe one student in this class don't know how to set up V sign.
I know how to set it up. I just want to make sure my value is right.
Well, if you set it up properly, your value's got to be right. I can imagine what problem y'all are having. I bet y'all ain't putting the right frequency into P-Spice.
I believe that's the problem. That they're not putting the right frequency, and I believe
Oh, okay. Well, why is it you don't know how to put what the right frequency is? Why don't you know what the right frequency is? That ain't got nothing to do with P-Spice. That has got to do with ELAT 120. You first see this sign equation in 120, ELAT 120. What is the frequency of this sign formula? You answer that, and then you'll find out the right frequency. You figure it out. I ain't gonna give you the answer because you should have known this from 120. Keep working on it. All right, where am I? So that's question one. That's question one. And question two of the final exam of last year. All right, let's do three. Let's do question three. And again, this is a definition. This is a definition, which you either know it or you don't know it. Okay. Determine all poles and zeros. That's what the question says, 1-1. Question 3-1. Okay. If you have a transfer function, then the zeros are where the numerator of the transfer function goes to 0. So 20 times s minus 3 times s plus 2 equals 0. The zeros of the transfer function is where the numerator goes to 0. The S values for the numerator goes to 0. And clearly, S equals 3 and S equals -10 are zeros. Any questions about that? That's just a definition. Now poles. Poles. That's where the denominator goes to 0. S squared plus 2s plus 5 equals 0. In other words, the roots of a quadratic, we have already found out the roots of this quadratic is s equals -1 plus j2 and s equals -1 minus j2. These are the poles. These are the poles. Any questions about that? Okay. Now, as simple as that is, some of you can screw it up because you won't study it.
So just to be clear, you're saying the poles is the same as the roots of this quadratic equation.
In this example, see, you didn't hear the definition of pole.
You say poles is when the denominator.
What did I say the
goes to
definition
0.
of pole?
When the denominator go to 0.
Thank you very much. When the denominator goes to 0. Okay. In this case, that's when s squared plus 2s plus 5 goes to 0. In other words, the roots of that quadratic. Now, suppose I did this. What are the poles?
Pardon me?
I added s plus 1. I'm asking you, what are the poles?
S equals -1, as well as the -1 plus j2 and the -1 minus j2.
Yes. 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 Why? Because when this goes to 0, and when this goes to 0, that's when the denominator goes to 0. All right. We can even do a pole 0 diagram. We can do a pole 0 diagram in Octave. Let me show you that. Okay. So let me just rewrite. Let me just rewrite the top. And then the bottom. So that's 20 s squared plus 7s minus 30 over s cubed plus 2s squared plus 7s plus s squared 3s plus 5. This 20 won't matter. We don't have to count that. So the numerator can be written as what? The numerator can be equal to 0, 1, 7, negative 30. And the denominator can be written as what? 1, 3, 7, 5. Agreed? All right. So pole zero diagram is you plot on the S-plane, you plot.
Godred, you can move the pen, please. Can't see that. Yeah, thanks.
All right. You plot the zeros. So there's a 0 that's equals 3. There's a 0 that's equals negative 10. You plot zeros with an O on the S-plane. You plot the poles on the S-plane. That's an imaginary number. That's its complex conjugate, and that's a real negative number. You plot it on S-plane, and the poles are shown with X's. All right. So let me go to okay. Can y'all see? No. You see, again, you go on ahead of what I'm doing. Why do students do that? I am not teaching you part B. I'm teaching you part A. Pay attention to what I'm doing. All right. The first thing we do in Octave is we load this package. Package load signal. The package is called signal. Okay. And then the second thing we do is we put an n. N is equal to, the numerator is equal to 0, 1, 7, negative 30. That's just what n is. For this example, that's what n is. Okay. And then the denominator is 1, 3, 7, 5. Okay. And now we say z-plane, comma n, comma d. And we have a figure. And there it is. Okay. There's the S-plane. Okay. There's the real numbers on the horizontal line, and there's the imaginary numbers on the vertical line. Okay, let's look at the zeros. What was zeros? The zeros was 3. There it is. See the 3 right there? Okay, and negative 10. There's a 0. There's a pole at what? Negative 1. See here, this is negative 1 plus J2 and negative 1 minus J2. And then there's another pole at negative 1. So this is called a pole zero diagram. And Octave will do it for you automatically if you put those things in right. Any questions about this? All right, I'm out of time.
Let me see the screen before this, please.
You mean how we computed it?
Yes, sir.
Yeah, just 4 lines. First of all, you got to make sure the signal package is loaded, and then you got to find n. This one in the middle here that doesn't count. You got to define n properly, the numerator properly, and the denominator properly, And this is command that creates the graph. Okay. All right. Again, I say to you, we covered a lot of material today. If you don't go now and study this material, you will not know it for Friday. And as you can see, we needed to know this material to do last year's exam. Any questions or concerns before I say goodbye? Okay, I'll see you all on Monday, God willing. Have a good weekend.
Hold on, Mr. Cartwright.
Yes,
So the extension would matter to us, right?
no. No. In lieu of that day that I gave you that project, the project that's due tomorrow at noon. So that's how we're making up that day.
We gotta make that one at 5 o'clock. Your daughter got right.
No, noon is fine.
Okay.
You know, man, I gotta grade these things, you know. You think I want to be,
It's just way to try. That's all. Okay, no.